Have you started the recording? Yeah. Sandip,
Okay, so shall we start Devendra then?
yeah.
Just a moment, I forgot to share the screen.
Oh, okay.
Yeah. Sandip,
Okay, so shall we start Devendra then?
yeah.
Just a moment, I forgot to share the screen.
Oh, we are listening ourselves, Devendra.
Something.
Some echo happened, but I think it is okay now.
Yeah, it is okay.
Okay. So, hello everyone. It's
Just a moment,
oh, sorry.
can you see the screen?
No. It disappeared. I thought that you. Okay, please.
Yeah, I think something happened. Just a second.
Okay. So then do you need to make him host or something if he's not able to share his screen?
No, see, there were... okay, just a moment. I'll have to log out and log in, it looks like.
Okay. Sorry.
Share screen. Bhaskara.pdf. I shared the text file actually. You know how much of a mess that is, Sandip, huh? I should not share the text. Okay, so can you see it now?
Okay.
Can you see the...
Yes. It is very well visible. So
Maybe you minimize.
Okay, I will.
Minimize.
Little bit. Not from.
Yeah.
That is perfect.
Yeah. So you used to have some click. Now, if you open it, goes to the next slides. Yeah. This correct.
Thanks.
It's getting a little bit cut from down, from bottom. So I don't know if
No, it is coming good. I think.
the bottom is not coming. It should be okay. Okay, Devendra. So, can you? Oh, sorry. Yeah. It's getting cut from the bottom, so maybe it will be. Yeah, if we can reduce little more, we can zoom out. Yeah. Just. Yeah. This much should be fine. Yeah, this is perfect.
Okay, I don't know where.
Maybe we can start with 18. Just I don't.
No, I wanted
2020.
17. Yeah, 17 is what I wanted. All right.
Correct. That's it. Yeah.
Okay, now we can.
Yeah, actually, this was also part of. Okay, so yeah, then I will formally start. So, hello everyone. It is of a great pleasure for me to chair this talk by my PhD supervisor, my Guruji. I thank Devendra for asking me to do this. I welcome you all to the second talk on cyclic covering of the projective line and arithmetic groups by Professor T.N. Venkataramana, who was introduced very well to the audience by Professor Dani at the beginning of the last talk. Hence, without having any delay, I invite Professor Venkataramana to show us today the proof of the arithmeticity of the image of the braid group under the reduced Burau representation.
Okay.
Over to you, Professor Venkataramana.
Thank you so much, Sandip, and thanks, Devendra.
Yes.
So let me very briefly recall what is happening. So I will not go through the entire thing that we did last time. So what we do is to look at this set of monic polynomials f of degree n with distinct roots. Okay, and I take for x the set of three tuples f, x, y with y to the d equals fx. So this equation is to be viewed as an affine part of the equation of a smooth projective curve corresponding to this f. So y to the d equals fx is a curve, but we are going to look at the compactification of this curve. This, so the normalization, I should be precise. So now, from the set of three tuples to S naught, the first projection takes a three tuple and send it to the function f. This yields a fibration whose fibers are smooth projective curves, in fact. So these are the cyclic curves of the projective line. So we can consider the monodromy representation of the fundamental group of the base on the first homology of this fiber. This fiber is, topologically it's the same, but these curves are all different, of course. So we have the monodromy representation of the fundamental group of the base, which we saw was the braid group on n letters. Excuse me. And this acts on the first homology of the fiber with rational coefficients. So this first homology of the fiber is also a modulo of the group Z mod dz, because Z mod dz acts on the variable y by sending y to y times a dth root of unity. If I replace y by y times a dth root of unity, this equation doesn't change. And this action of Z mod d commutes with the monodromy action on the H1, and therefore, you could look at the part of the H1 which is an eigenspace for the action of the Z mod d. So instead of taking H1 with Q coefficients, if I look at H1 with complex coefficients, then the following proposition is true. The monodromy representation is the direct sum of the reduced Burau representation, well, with a bar on it, which I explained last time. I don't want to do it again, but that bar is important because it's important even in the proof. So it's the same as the reduced Burau representation at eth roots of primitive eth roots of unity if E does not divide n. If E does divide n, then this will contain a trivial copy. Rho E of n will contain a trivial copy. I have to go modulo that to obtain this bar. So the monodromy representation is related to the reduced Burau representation. So the arithmeticity of the monodromy follows from the arithmeticity of the image of the reduced Burau. And so without any further mention of it, I'm going to look only at the reduced Burau representation, rho d of n, and conclude something from, conclude the arithmeticity. So I don't know if I mentioned this, that it's preserving a Hermitian form, the braid group preserves a Hermitian form. Maybe I did. So let me just re-explain this. So a Hermitian form is to be viewed as a Hermitian form or a free module over this ring of rank n-1, this one, R to the n-1. But this ring itself comes equipped with an involution f to f bar, which is given by q goes to q inverse. So on this R to the n-1, which was really the abilinization of a certain kernel, there is a Hermitian form which you define like this. The ith basis vector is orthogonal to the jth basis vector if the surfaces psi and j are far apart. If they are the same, then it is q plus 1 square upon q. You can see that this is invariant under q goes to q inverse. I didn't verify this. And the inner product of ei with ei plus 1 is minus q plus 1. So you can check that this edge is preserved by the action of the braid group. So if I look at R0 to be the subring invariant under this conjugation, the real elements, then the Burau representation has image in the unitary group which is a group scheme over this ring of real elements of R. So this is a group scheme. The unitary group is a group scheme, and you are looking at the image of the braid group, which takes values in R0 points of this group scheme. So I'm recalling some bits from last time because I'm forced to do so. So now, instead of considering the ring R, this R was, Laura polynomials in one variable with integral coefficients. So instead of looking at the ring R, I look at the ring R modulo the cyclotomic polynomial of degree D in Q. So this quotient is very easy to check that it's the ring of integers in the D cyclotomic extension of Q. So as I mentioned earlier, this D module, E D to the n minus 1 is irreducible unless D divides n. I believe Professor Broomer was asking what happens when D divides n. And in fact, it's important to us when D divides n, this module has a trivial subrepresentation whose quotient is denoted rho n d bar. So the Hermitian form itself descends to a Hermitian form on this, and it's non-degenerate if D does not divide n. If D does divide n, then it's degenerate, and the trivial module, I said it preserves a trivial subrepresentation. The trivial module is the kernel of this Hermitian form. If I go modulo the kernel of the Hermitian form, I get a non-degenerate Hermitian form by definition on this quotient. So this quotient also admits a non-degenerate Hermitian form, which is invariant under the braid. So the irreducibility of rho and D implies that HD bar coincides with the Hermitian form, which was defined on the H1 part of the curve. So that's the proposition which relates the Burau representation to the monodromy. So finally, this is what we are to prove. So I look at the D cyclotomic extension, look at the ring of integers there, and in here I look at RD star, which are the ring of integers in the totally real subfield of the cyclotomic field. So we now have the situation that the reduced Burau representation evaluated at D takes the braid group into UH of RD star. It should have been RD star, sorry, which is contained in GL n minus 1 of RD. So the theorem is that if n is bigger than 2D, then the image has finite index in this arithmetic group. In particular, the image of the Burau representation is itself an arithmetic. So I remarked earlier that in this range, already in the range n greater than D, one can show that the image of rho n of D contains unipotent elements. And the theorem is proved by showing that you get a big chunk of unipotent elements. This big chunk is what I am going to explain now. And then we can appeal to some general results of Raghunathan and myself on the arithmeticity of subgroups of higher rank congruence arithmetic groups, which are generated by opposing integral unipotent radicals. So for the next few minutes, I will be talking about this result of Raghunathan and myself, because I'm sorry to keep talking about very old results, but this is what we have to use in order to prove this theorem on arithmeticity. So to explain that result, let's begin with an example. So let's look at the simplest possible group, SL2Z for us. So given an integer m, I'm going to look at U plus of mz and U minus of mz. What is U plus of mz? It's just the upper triangular unipotent elements in SL2 which are congruent to identity modulo M. These are integral elements. And similarly, U minus mz are lower triangular unipotent elements which are integral and which are congruent to identity modulo M. So I denote by G sub G bracket M the group generated by U plus mz and U minus mz. So one can show that this group has infinite index, but it's Zariski dense. That's not hard to show. This GM is Zariski dense but has infinite index, and therefore, by our definition, it's not an arithmetic group. You have a subgroup of SL to Z, explicit subgroup, which is not an arithmetic group. This is a small exercise, but it can easily be verified. But now suppose I replace SL2 by SLn, n greater than or equal to 3. So I similarly look at
excuse me, for m is equal to 3 also, no? This is not known whether
not known. I don't want to discuss that. You know it very well, so I won't. No. So it's all right. So we'll come to that. So let us look at n greater than or equal to 3, SL3Z or SLNZ. Okay. So U plus MZ denotes the group of upper triangular unipotent matrices which are congruent to identity modulo M. And U minus MZ similarly denotes the lower triangular integral matrices which are unipotent and congruent to identity modulo M. But this subgroup generated by U plus MZ and U minus MZ has finite index. It's not entirely trivial actually. It's this theorem uses the fact that SL and Z has the congruent subgroup property. This was a theorem by Bass, Binner and Serre, and TITS uses that to prove this. So TITS also proved a similar result for the symplectic group SP2GZ. Yes, Sandip was asking me, you know, I had stated a result of Ocampo that in the case when you have hyperelliptic curves, y square equals x minus a1 into x minus a2 into x minus an, ai are all distinct. So in that case, Ocampo proved that the monodromy group goes into the symplectic group, integral symplectic group, and it has finite index there. And he used this particular result of TITS to prove this. So the condition n greater than or equal to 3 and g greater than or equal to 2 means that the real rank of these groups, SLN and SP2G, is at least 2. So these are what are called higher rank arithmetic groups. Actually, in this case, it's true that even the Q rank is at least 2, but we don't need such a strong result. We need only that the real rank is at least 2. So those are what are called higher rank groups. For example, SL2 Z root 2 is a higher rank group, although the Q rank is 1. SLN of Z is a higher rank group because for n greater than equal to 3, because the rank of SLN, real rank is n minus 1. The real rank of SP2G is G. So this theorem of TITS can be generalized to all semisimple algebraic groups. So let us make some assumptions. Start with a linear algebraic semisimple group, which is Q simple in the sense that there are no normal algebraic subgroups which are defined over Q. That's what is Q simple, with real rank at least 2. So we're going to also assume that the Q rank is at least 1. Otherwise, you will not get unipotent elements. So this is an important assumption to get unipotent. So then G has unipotent subgroups defined over Q. So I start with a parabolic subgroup like the upper triangular group that I mentioned earlier. We start with a parabolic subgroup of G, and then take its unipotent radical, and take the opposite unipotent radical, that is unipotent radical of an opposite parabolic subgroup. In the case of SLN and sp2G, we are going to look at upper triangular group and the lower triangular group. They are opposed to each other, but there is a notion of opposition in general. I don't want to explain too much because that will go somewhat far away from what we want to do today. So again, for an integer m greater than or equal to 1, we are going to define Gm to be the subgroup of Gz generated by the groups u plus mz and u minus mz, where u plus mz are elements which are congruent to the identity matrix modulo m, G of z. So this is the notation. Then one has the theorem. Under these assumptions, this group Gm has finite index in Gz. So the group generated by congruent subgroups of opposing unipotent radicals is itself an arithmetic group. And insofar as I know, this is the only test which tells you when a subgroup is arithmetic. Because, suppose you are given a subgroup of SL and Z, how to test whether it's arithmetic or not. And this is actually a difficult problem. In some sense, it's not a solvable problem, because there is a result, an old result of Mikhailova, which says that it's not a decidable problem at all. So this is one of the few criteria which tells you when a subgroup of SL and Z is an arithmetic group. If it is generated by congruent subgroups of opposing unipotent radicals, and these congruent subgroups, these unipotent radicals are contained in a higher rank group G, rank at least 2. That's very important. If the rank is not 2, this is not true. So the real rank is at least 2. That's important. So as I said, it's somewhat ancient by now. So, but you see, we are not going to look at integral groups, GZ. We are going to look at groups with coefficients in ring of integers of some totally real field. So we want to identify such a group with a group like this, G of Z. So this identification of the, for example, unitary group with coefficients in a ring of integers of a totally real field with a group like this, G of Z, this is achieved by what is called restriction of scalar procedure. So which I want to explain a little bit. So to explain this, let me again begin with a simple example. Let's look at SL2C. So you can think of it as a real group which commutes with scalar action by C on the vector space C to the 2, but C to the 2 is just 4-dimensional real vector space. So you can think of SL2C as a subgroup of SL4R which commutes with the action of C. So similarly, if I have K over Q, a finite extension of degree K, an algebraic group script G contained in GLM defined over the number field K, you can view this as an algebraic group ordinary capital G contained in GL M times K. Here, this is 2 into 2, 4. C squared has been identified to R to the 4. Here, K to the M has been identified to Q to the Km, where K is the degree of capital K over Q. So this you can think of as an algebraic group in GLMK, which commutes with the action of K as scalars on K to the M. K to the M is viewed as Km dimensional vector space OQ. So this procedure of getting from script G to capital G is called the restriction of scalars from K to Q, and you write like this. Capital G is R, K over Q of script G. So if OK is the ring of integers in K, then script G of O of K, this is some kind of a group, and this has finite index in the actual integer points here. Remember, we were identifying such things as arithmetic groups, but I'm saying this is the same as this. This is also an arithmetic. So if script Q plus and minus are unipotent radicals of two opposite parabolic subgroups defined over K in script G, then I take their respective Weil restriction of scalars. I get two unipotent groups, U plus and U minus. These are unipotent radicals of two opposing parabolic Q subgroups of G. So what's more, the real points of this group G are just the script, take script G, but look at K tensor R over Q. This algebra, the this group is isomorphic to the group of real points of G. That follows easily from this definition. So the theorem that I mentioned earlier takes the form: if script G is a simple algebraic group defined over a number field, and script Q plus minus are unipotent radicals of opposite parabolic K subgroups in G, and if the real rank of G is at least 2, then the congruent subgroups generate finite index subgroups of G of OK. That is, the group generated by U plus MOK and U minus MOK is a finite index subgroup here and is therefore an arithmetic. So I want to apply this to unitary groups. So I start with a totally imaginary field E. I assume that this totally imaginary field is a quadratic extension of a totally real number field, capital K. So I have a map from E to the N cross E to the N to E, which is a K bilinear form, which is linear in the first variable and conjugate linear in the second variable. You see, the complex conjugation on E leaves capital K pointwise fixed, and it gives you the non-trivial Galois automorphism of capital E over K. And so I can talk about conjugate linear, and so such an H which is K bilinear and linear in first variable and conjugate linear in the second for E is called a Hermitian form. So if I have two linearly independent vectors V and W such that the Hermitian form has the property that V is orthogonal to itself under the Hermitian form, so is W, and V and W are mutually orthogonal. So you have a two-dimensional subspace of E to the N where H is identically 0 on this two-dimensional subspace. So then you can look at the unitary group, which is an algebraic group over K, and the real rank of this restriction of scalars you can show is at least 2 under this condition. Actually, under this condition, the Q rank is at least 2. So let's look at the subgroup P, which leaves the line through E fixed. Line, only the line, it preserves the line. So you can show that this P is a parabolic subgroup of this unitary group, and the subgroup U fixes this line. Of course, once it fixes the line, it stabilizes the orthogonal complement of this line as well. And this, of course, it stabilizes all of E to the N. So it leaves the flag stable, but it acts trivially on successive quotients. That is the unipotent radical. So the result that I mentioned earlier a corollary of this is the following. If I start with a Zariski-dense subgroup of G of OK, which contains the congruent subgroup U of M OK for some U plus of M OK, then gamma has finite index in G of OK and is therefore arithmetic. So all you need to do, if you already know gamma is Zariski dense, is to prove that it contains integer points of a congruent subgroup of the unipotent radical of a parabolic K subgroup. Then you know it's arithmetic, provided this higher rank assumption is true. Okay, so this is how we will apply this. So let's return to the reduced Burau representation rho and D at D roots of unity. As I said, it preserves a Hermitian form, and when D divides N, the form is degenerate since the kernel is one-dimensional. So the unitary group scheme, yeah, this I didn't motivate, but it's easy to check that the unitary group of this Hermitian form, in the case when it is degenerate, is no longer reductive, but it is a semidirect product of a vector group with a reductive group. All right. So the vector group is the kind of unipotent part of this non-reductive group. So the vector group of the unitary group defined over the real ring Rd star is actually Rd to the n minus 1. That is the vector part. And this is the reductive part. Okay, so let us see what it looks like in terms of matrices. Sorry. So you see, this was just to tell you what when the Hermitian form is degenerate, when D divides N, what happens? But in general, you have a unitary group, and I would like to understand how the center of the braid group acts under this Burau representation. Okay, so I'm going to explain that first. Rather not explain, just recall the action. So let's look at this. We had some generators for the braid group, S1, S2, Sn. So I'm going to look at S1 first, then the next element S1, S2, then the next element S1, S2, S3 up to Sn minus 2, then the last element S1, S2, Sn minus 1. So the product of the first n minus 1 elements followed by the product of the first n minus 2 elements and so on up to this. Now this element has the property that its square generates the center of the braid group. This is a computation, it's not very difficult. So this element has a kind of topological meaning, but this is called the Garside element. Topologists really like this element. I don't know why, but they have very important consequences arising from its action on various representations of the braid group. So on the Burau representation rho n, this central element acts by the scalar q to the n. So we denote this element by Cn if the dependence on this n is to be spelled out, because we are going to look at braid group on n letters containing braid group on n minus 1 letters and so on. So because of this, we sometimes instead of calling it C, we call it C sub n, just to show how it depends on n. So if it acts by q to the n on the Burau representation, on the quotient representation rho n of d, the action of q is by omega d, where omega d is the primitive d root of unity, because q goes to a primitive d root of unity in rho n of d. So consequently, the action of q to the n is trivial on rho n of d if and only if d divides n. because if D divides N, Q to the N equals 1. And if Q to the N equals 1, and Q is a primitive d root of unity, that is how we got this representation. If you have a primitive d root of unity, its nth power is 1, if and only if N is divisible by D. So suppose N is divisible by D, the central element Cn minus 1 acts on this quotient rho and D bar. But you can easily check that this quotient restricted to the braid group and one letter less is the Burau representation on one letter less. It's just the Burau representation. That's not hard to check. And therefore, it acts by a certain scalar, Q to the N minus 1, which is Q inverse, which is omega D inverse. And therefore, it is not equal to 1. It's very important that the scalar be not 1. And that is what is true. So now let us look at the reduced Burau representation rho n D when n is divisible by D. You see, I should have put that in matrix form. I had written the unitary group as a semidirect product. That semidirect product takes that extra, kernel vector to itself, and its matrix form looks like this: 1, 0, V, and some matrix here, rho n minus 1 D bar. The unitary group itself looks like 1, V, 0, and something here. But we have this element Cn minus 1, which looks like 1, 0, 0, and a scalar here. So 1, V, 0, 1, commutator, if I look at its commutator with 1, 0, 0, 1, lambda, where lambda is a non-trivial scalar, when I look at its commutator, everything here disappears. I just get the identity. So I just get a vector here. Okay, so I should have made that computation, excuse me. The element Sn minus 1 looks like 1, V, 0, some stuff here. The element Cn minus 1 looks like 1, 0, 0, lambda here. So when I take the commutator, that lambda being a scalar commutes with everything here, so I get identity and I get a certain vector part. This is the crucial computation. So I ought to have made it, but sorry. But the most important thing is that this vector part is non-zero. You can show that. So you got, therefore, one unipotent element in the Burau representation. Correct? Exactly one unipotent element you got. But now you see the entire Bn minus 1 looks like 1, 0, 0, some stuff here. That also operates. And upon taking conjugates of this 1v01 by the elements of Bn minus 1, I get lots of unipotent elements. Okay. So by taking commutators of this U sub V with elements of Bn minus 1, I get lots of unipotent elements uv prime, where v prime runs through an arithmetic subgroup of this vector group. So I get a whole lattice worth of elements here in ed to the n minus 1. So yeah, I do have some time. So when n equals 2d plus 1, that is when d does not divide n, I mean patently. So let's look at this representation rho n. But when I restrict it to Bn minus 1, n minus 1 is indeed divisible by d. When I restrict it to Bn minus 1, this rho n has a sub-representation isomorphic to rho n minus 1, and with quotient being trivial. This is an easy computation. But we just now saw that rho n minus 1 is a kind of a semidirect product. The image is a semidirect product group. So the same holds if rho n is replaced by rho n of d. So if n equals 2d plus 1, then rho 2n plus 1d restricted to braid group on one letter less has the sub-representation rho 2d of d with trivial quotient, with a trivial quotient. Yeah? But this representation itself is not irreducible. It has a trivial sub-representation because d divides n. D divides this 2d. It has a trivial sub-representation with quotient rho 2d d bar. So viewed as a sub of this, so you have a vector part v here, and when you view it as a sub of rho n, it acquires a certain tail here, which gives you a v star, and there is some disturbance here which we won't care about. So you get matrices of the form 1 v star 0 1 n minus 2 v star 0 0 1, where v star actually depends on v linearly. So it's really this v part which is embedded like this. So to repeat, bn minus 1 has a sub-representation where the matrices look like this. But when you look at it as a sub-representation of this representation rho n, it has the matrices become larger, they look like this. You're only looking at this part for rho n minus 1. If I want the full representation rho n, I have to add something. But so let us look at this. This is the vector part has become like this. This is actually the unipotent radical of a parabolic subgroup. It preserves this vector, it preserves the orthogonal complement, and it operates trivially on successive quotients. So it's really the unipotent radical of a parabolic subgroup. Because of the conclusion of this slide, this one, we get that the image of rho and d contains an arithmetic subgroup of the unipotent radical. Now, when n equals 2d plus 1, one can check that the rank is at least 2. Okay. In fact, the Q rank is at least 2, not just the real rank. Q rank is at least 2. So by using that result of Raghunath and myself that I mentioned earlier, we then see that the monodromy group itself is arithmetic if n equals 2d plus 1. So our goal was to get a unipotent radical worth of elements in the monodromy group, which we got. Once we do this, then this result applies. Then we can prove arithmeticity for this case. Now, what happens when n is bigger than 2d? Once you prove it for 2d plus 1, you can establish the general case, arithmeticity is the general case for induction. Okay. So I don't want to give you too many details because this is actually fairly routine, but the non-trivial case was really this part. Once you got this, the rest of it could have been done quite easily. Okay, but now we were, if you remember, we were looking at very special case of cyclic extensions where the equation looked like oh God, where was I? Y to the d equals fx, where fx had no repeated roots. But when fx does have repeated roots, you still have an analogous theorem, but under a somewhat strong assumption. So general cyclic case. So I take S to be the subset of C to the n, which is the Zariski open set of n tuples, alpha 1 through alpha n of complex numbers, which are all distinct. So then I fix integers k1, k2, kn, and b such that these don't have common factor. So given a point, I get a cyclic cover as before. So as alpha varies, we get a family of cyclic coverings, and we wish to understand the monodromy representation or the fundamental group of the base on H1 of these cyclic covers. But this, suppose I look at this set S of complex numbers with distinct entries. I can form a monic polynomial out of this with distinct roots, namely x minus alpha 1, x minus alpha 2, x minus alpha n. So we get a morphism from S to S naught given by this n tuple goes to that polynomial with alpha 1 through alpha n as roots. So this is actually a covering map, as you can easily see. Right? So the fundamental group of this S naught, we know what this is. This is the braid group on n letters. So we have this quotient map Bn to Sn because this is the covering map. So the kernel of this map Bn to Sn is what is called the pure braid group, a colored braid group. So I recall that Bn had generators S1 through Sn minus 1 with certain relations, the braiding relations and the commuting relations. If I impose this additional relation, Si square equal to 1 for all I get the symmetric group, and Pn is the kernel to this quotient. So it is the pure braid group. So we have identified at least what the fundamental group of this S is. So now one has to understand what the monodromy representation looks like in the general cyclic case. So previously I looked at a certain abelian quotient f to q to the z where all the special generators xi went to that particular q. But now I look at the entire abelianization, not just q to the z only. So look at the whole abelianization. So it has a certain kernel that is the commutator subgroup of F. So the abelianization of the free group on n letters, x1 through xn, is the free abelian group on these n generators, correct? So we can write this multiplicatively. So xi is the image, capital Xi is the image of little xi under this quotient map. F goes to FAB. So FAB, you can write abelianization as x1 to the z dot 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 xn to the z. So the group ring of this is the ring of Laura polynomials in n variables. So the group ring of this guy is the ring of Laura polynomials in n variables. So again, I can look at the abelianization of this commutator subgroup. On this abelianization, F operates by inner conjugation. But n itself operates trivially on its abelianization because we have made it abelian. So on the abelianization of n, the abelianization of F operates. So the group Bn operates on this exact sequence and therefore stabilizes n, and therefore it acts on n abelianized. So n abelianized is also a module over F abelianized, and therefore it's a module over this group ring, integral group. But Bn does not commute with this. You know, if you look at what Bn does, each of these generators, Bn acts via Sn by permuting these coordinates x1 through xn. You can check that. So the action of the pure braid group only commutes with R. So this is, of course, this is an integral domain. So I can look at the quotient field of this integral domain. Yeah, previously in the case of the Burau representation, we had an abelianization of something, that kernel, which was a free module over some analog of this ring R. But now the abelianization is no longer a free module. That's the problem. It's actually quite a complication. So, but this abelianization is a submodule of this vector space. So we need to replace this abelianization by something else, which I'm going to do. So this abelianization contains the commutator element xi xj, because if I look at this commutator element in the free group, its image is trivial in the abelianization of F. So n-ab tensor omega contains this element, and it also contains this element, because I'm allowed to invert certain elements in the ring R. So I'm going to invert this. So if I look at the R submodule generated by these Vij's, this one can show is a free R module, and also that it's stable under the pure braid group. So this R module is called the Gassner representation, G sub n. So the Gassner representation yields a homomorphism of the pure braid group into GL9 minus 1 of this. Now again I look at the cyclotomic extension of Q, which we obtained as ZQQ inverse modulo phi d of Q. In the previous case, we sent all the generators Xi to Q. Now I am going to send this generator to Q to the Ki. Each Xi is sent to Q to the Ki, given this n tuple. So I get a homomorphism of Pn into GL n minus 1 of this ring of integers. I'm going to denote this GNDK, and this is the Gassner representation in these roots of unity, and it depends on K. So one can show that the Gassner representation is irreducible if and only if the sum is not divisible by T. If all the Ks are equal to 1, then this is equal to n. If and only if n is not divisible by D, the Burau representation was irreducible. So it is an analog of that. If it is divisible by D, then it contains a trivial submodule, and the quotient is an absolutely irreducible representation. So this is called GNDK bar. So we have an analog of that earlier proposition. The monodromy representation is a direct sum as E runs through the divisors of D of the reduced Gassner representations. Here I made a strong assumption. I would like to prove it without, but I am not able to do it. So all the Ki's should be coprime to D. That's when this is true. All the Ki's are coprime to D. Then this is true. And so the arithmeticity of the image of the monodromy representation will follow from that of the image of the Gassner representations at roots of unity. So this is established similarly to proof in the case of the Burau representation. So, and of course, this computation is much more complicated, but quite analogous. I think this is where I will stop. Thank you.
Yeah, thanks a lot for giving this series of two very nice lectures. So you all, thank you very much. So is there any question or comments or remark?
Okay.
Okay. No, I have just one question. I don't know. It's like how. Is it means like you gave the proof of the arithmeticity of the image of the braid group under the that reduced Burau representation?
Yeah.
So was it already known or that image is Zariski dense or once arithmetic it will be Zariski dense? But I saw that in the proof you gave that it like sort of. It contains U plus MZ. So how does it contain the U minus also for the Zariski denseness?
The thing is, one knows that the monodromy representation acts reductively. Okay, that is a generality. Monodromy is reductive because the representation is essentially irreducible. You know, we are, once it's irreducible, you have the Zariski closure is reductive and it contains such a large unipotent radical, then it is all of GLN. So therefore it is Zariski dense, not GLN, all of SLN, and therefore it is Zariski.
Yeah, in this case maybe UN.
Well,
UN. Okay.
Not really UN,
okay.
Because the connected component of identity, it's not UN, it's contained in UN. It's not UN, it's semi-simple. The Zariski closure is always semi-simple, not necessarily connected. So it is contained in UN, it contains SUN. So the Zariski closure contains SUN. Okay, and that is good enough. That's all that we need.
Yeah.
Because the result is about semi-simple groups. Yeah. So therefore it contains opposing unipotent radical once it's reductive. Yeah, that's a relevant point. But the proof uses the fact that it contains such a unipotent radical. By the way, there are cases when the image is not Zariski dense. The image could be finite. There are cases for which the image could be finite. So therefore, that assumption that n greater than d is important for even Zariski density.
Very nice.
Okay.
Thanks. Is there any other question or remark?
I don't know. Where should I look at the chats? Maybe there are.
No, there are no questions on chat. I have been looking at it. Oh, someone just now wrote. Yeah, Professor Brumer again. So what is known about the endomorphism of the Jacobians of the curve y to the power d is equal to fx?
Oh, I don't know. I think it is just the ring of integers in the d cyclotomic extension itself, but maybe it is more. It could be more than that. I don't know actually. Yeah, that would be. It's not very clear if the monodromy group commutes with the full endomorphisms, but it commutes with these endomorphisms only. Yeah, maybe it is just the endomorphisms which arise from the ring of integers in the d cyclotomic extension, but I could be wrong, Oh, excuse me, if you can look at the full Jacobian, it's a product of a ring of integers in the eth cyclotomic extension where E divides D. It at least contains that much. Whether it contains more than that is not clear. Yeah. I'm not able to see the chats. Why?
Maybe you just need to move your cursor.
Yeah, I saw it now. So it is not just the ring of integers in this cyclotomic extension, but it's the product of ring of integers in the each cyclotomic extension. E divides D. That full product is contained in the endomorphism. Yeah, no problem.
Yeah, my question was really whether one understood anything about when one might expect larger endomorphism, right? Does one know anything about the subspace or subvariety where you would have a jump. I think certainly if the polynomial f is separable, it's very likely that generically you will get only the cyclotomic fields.
Okay. Okay.
But I'm curious about finding examples, in fact, where you get larger. So this would be a proper subset.
Oh yeah, that's
of
right.
your.
Yeah, this would be a proper subset. Yeah, I don't know. Of course, what one can say is that the monodromy group, it's not clear at all that it will commute with the larger endomorphism ring. That's not clear.
Okay.
Yeah.
Well, thank you. I enjoyed your lectures.
Thank you.
Very interesting.
Thanks.
Devendra, you are muted. You unmute yourself before saying something.
Yeah, I say that Kit is very good lectures, and there are a lot of material to understand over the time and come back again. Okay, Sandip, again, thank you to you for chairing this session.
Yeah, thanks, Devendra, once again for
Thanks, Professor
asking me.
Venkataramana, for these nice lectures, I think.
Thank you.
We will see you again in this program, maybe if time you realize.
Yeah, sure.
Thanks a lot. I also really enjoyed listening this to me. I can get some. Okay.
Okay.
Okay.